Okay.
Dear friends, we start the
Possible to plug the computer?
next lecture now. Professor Benedict Gross, who is the George Wassman Leverett Professor in Harvard and a well-known number theorist who did his PhD, Professor John Tate.
No, not yet.
And of course, practically every number theorist knows his name, but I don't know others. I mean, of course, a number theorist would have known about Gras-Zagier formula or Gras-Kobrich theorem and so on. Yeah, yeah. And he has got many awards, and I am not going to stand between you and him giving these awards, etc. But he got his Cole Prize in 1978, MacArthur Fellowship. He is a member of the American Academy of Arts and Science. He is a member of the National Academy of Sciences. And very recently, he has also become one of the board of trustees of Institute of Advanced Study. And that much introduction would be sufficient about him as an academician. But let me say a little more about his connections with India and in particular Madras. He did spend a little long time in Chennai, when of course we did not have an occasion to invite him for such a lecture, for two simple reasons. And the number one, that it took place a few years back, more precisely 1971, where most of you might not have even born. And the second reason was that his visit was not regarding mathematics, but one of his other interests, namely music. And that was here in 1971. And regarding the Indian connection, I should probably most of you would have known that the leading number theorist from India, Professor Deependra Prasad, is one of his doctoral students. With this introduction, let me request him to start.
Thank you, thank you. So I'm going to speak about number theory and maybe address the question that people had on Fermat's last theorem. So before there were cubic equations, there were quadratic equations, and the most famous quadratic equation comes from the theorem on the sides of the right triangle, which in the West we call the Pythagorean theorem. Here's a bust of Pythagoras, but Pythagoras is really a mythical figure. We have really no evidence of his existence at all, and all of these busts are just people imagining what Pythagoras might have looked like. Andre Weil, who's quite knowledgeable about the history of mathematics, says that the status of Pythagoras in Greek mythology is about the same as the status of Prometheus. In any case, the theorem was discovered earlier in India. There's a sutra of Badhayana earlier, which refers to the Pythagorean theorem. But before one gets into a dispute as to whether this was discovered in Greece or in India, it actually was discovered much earlier. We'll be studying solutions of this in the rational numbers or the integers. So if you look at the first few solutions, which are over the integers, are 3, 4, 5, and 5, 12, and 13, 7, 24, and 25. But there are many more solutions that are inscribed on a Babylonian tablet that's almost 4,000 years old. This may be one of the most famous pieces in the history of mathematics. It's not much larger than that, and you can find it in the Columbia University Museum, and it's we don't really know where it comes from. It may have been an exercise book back in ancient Mesopotamia, but it was analyzed by the great mathematical historian Otto Neugebauer, and you'll find inscribed on this tablet these other solutions of this famous quadratic equation. These are called, by the way, Pythagorean triples. They're integer solutions so they're right triangles with integer sides. And it seems pretty clear from the existence of this tablet that the Babylonians knew the general form for a solution, and there are infinitely many solutions to this quadratic equation. And that's a general phenomenon. If you have a quadratic equation over the rational numbers, there either is no solution at all, or there are an infinite number of solutions. But, whoops. let's get rid of that. Let's not do that. That was a bad idea. Let's cancel that. Okay, good. Let's try another button. But I'm not going to talk about quadratic equations. I'm going to talk about cubic equations. So cubic equations, here are two of the most famous cubic equations. The first is what's called the Fermat cubic. X cubed plus y cubed is 1. And the second one is an equation that was studied by Mordell, and it's when the product of two successive integers, y times y plus 1, is the product of three successive integers, x times x minus 1 times x plus 1. And cubic means that one of the variables in the equation appears to degree 3, as opposed to quadratic equations. And what's interesting about cubic equations, what makes them the most interesting equations in two variables, is that unlike quadratic equations, you can either have a finite number or an infinite number of rational solutions. And the main question in cubic equations is trying to decide, given an equation, whether you have a finite number or an infinite number of rational solutions. For quadratic equations, as I said, you almost always have an infinite number of solutions. And for equations of degree greater than 3, Gerd-Faltings proved that there are only a finite number of solutions. But cubic equations are right in the middle where you could go either way. So the first equation here, the Fermat cubic, Fermat claimed and Euler proved that there are only two solutions of that in the rational numbers, where x is 0 and y is 1, and where x is 1 and y is 0. And that's that case of Fermat's last theorem. And for this equation, we're going to see that there are infinitely many solutions in the rational numbers, and we're going to see how to produce them. So in this case, the modern subject was started by Fermat, and we actually do know what Fermat looked like. He lived in the 17th century, and he was a magistrate in Toulouse. At the time, nobody was a professional mathematician, but he had an extensive correspondence in his time and tried at one point to persuade Pascal to write up his work, which would have been a wonderful thing, but no one actually did. And so Euler had to almost recreate it from scratch. So Fermat had a wonderful method of producing new solutions of cubic equations from old ones, which I'll show you and is the basis of the subject. And it all comes from studying the graph of the solutions and the intersection of the graph with a line. So here's this equation that I mentioned, the second equation, y squared plus y is x cubed minus x, and I've graphed in the real plane. The blue indicates the graph of the real solutions of this equation. So these are the values x and y that satisfy this equation. And we're interested in finding, among these real solutions, we're interested in finding where we have x and y have both rational coordinates. That's the problem, the arithmetic problem of solving cubic equations. So the key thing about a cubic equation is that when you intersect it with a line, you get three distinct points, right? I mean, if I took the line for here, if I intersected this with the line y is mx plus b, and I substituted that value for y into here, I get a cubic equation in x. And over, say, the complex numbers, that has three solutions. And for every x, which is a solution, I take the other point on the line, y is mx plus b, and I get the point on the graph. So let's see if I can do this. Here's the intersection of the graph with a line, and you see the 3 points. If you intersect the line with a quadratic equation, you get 2 solutions. You intersect it with a quartic equation, you get 4. But 3 is the magic number. And the reason is that if 2 of the points on the line which meet the curve are rational, namely if these two are rational numbers, then the third point of intersection is also a rational solution. And the reason is very simple. Suppose these two are both rational solutions, then the line through them has a rational slope and a rational y-intercept, right? And so when you substitute it into this equation, you get a cubic equation in x with rational coefficients. And the sum of the x values which are solutions is a rational number, and 2 of them are rational numbers, so the third has to be a rational number. And that shows that this 2 is a rational number. And then since this is on a rational line, if x is a rational number, so is y. And so this gives a way that Fermat discovered of propagating 2 rational solutions and finding a third. You take the line through them, and you take the third point of intersection. And Fermat, who is also one of the originators of calculus, knew that if you let the 2 points come closer and closer together, the secant line that you had, which in this case goes through the 2 points, becomes a tangent line, which intersects the curve doubly at the point, say -2 and -3, and then that intersects at a third point, which will also be a rational solution. Now we're starting to get some denominators in the rational solution. And so Fermat could start with some very simple solutions of a cubic equation, and by this process, which became known as the chord and secant process, or the secant and tangent process, produce more and more complicated solutions. So for example, if you start with this curve and you start with the two solutions, 0 and 1, and you take the line through them, you got this 2 minus 3, and then you start taking chords and tangents, you produce these very complicated rational solutions. This is the x-coordinate, and that's the y-coordinate. And Fermat loved this because what he would do in the mathematics of the time, you didn't actually tell anyone what you were doing. You would just send a challenge problem over to another country, and since Fermat was French, the challenges usually went to England, and you'd say, I found this, this solution, and can you find a larger one, or something like that. And of course, he wouldn't tell what his method was. You had to deduce the method. Now, these solutions are growing at a very nice rate. You can see it's almost a parabola here, and in fact, that's something called the height of a rational number, and the height of the rational number is essentially how much paper it takes to write it down. It's how many digits it has. And you see the height is growing quadratically when we apply this secant and chord process. And that's actually a theorem, a beautiful theorem about the heights due to Andre Weil. All right, now, however, you might get the idea from this equation that once we could find some simple solutions like 0, 0, and then apply this process and find, and it turns out you get every rational solution of this equation from this process just starting here and doing the chord and tangent process. But what's really challenging about cubic equations, which are also called elliptic curves, is that even the first solution may be very difficult to find. So here's an equation where the coefficients are a little larger, but they're not that large. You know, we're talking about numbers of 15 digits, where the smallest solution, there are an infinite number of solutions, but the smallest solution, the x-coordinate, has 5,000 digits in the numerator and in the denominator, and the y-coordinate is much more complicated. So you can imagine that this solution was not found by trial and error. We had to have some systematic way of constructing solutions of cubic equations, which I'll discuss a little later in the lecture, and that systematic way was used to produce the solution of this equation. Okay. Now, let me tell you what the most important invariant is of a cubic equation, which is called the rank. And since we're not giving a formal mathematical talk, and I'm not supposed to use words like finitely generated abelian group, I'll just say that the rank is essentially the number of independent solutions you need to get all of them from this chord and tangent process. So these two equations, this one and this one, turn out to have rank 1. You have to find one solution, and then you can generate all of them from this geometric way. But of course, there might be more. You might have to produce 2 independent solutions before you got more. So if the rank is 0, that means there are only finitely many solutions. That's why I say essentially the number. It's up to finitely many solutions. And if the rank is positive, that's the condition that there are infinitely many. So this crude question that we had, does an equation have a finite number of solutions or an infinite number of solutions, can be made more precise by saying, okay, what is the rank, or for the mathematicians, what is the rank of the group of the abelian group of rational solutions? And you can make curves which have higher and higher ranks. So here's a very simple family. Y squared plus y is x times x minus 1 times x plus a. If you take a equal 1, that's the curve we've been doing. And if you take a is equal to 0, 1, 2, 4, or 16, you get curves of rank 0, 1, 2, 3, and 4. So by just changing the coefficients of a curve in a simple way, you can, by trial and error, produce curves of higher and higher rank. And the big theorem in the subject was proved by 2 mathematicians in the early part of the 20th century. This is a picture of Louis Joe Mordell, who was an English mathematician. Well, he was a very proper Englishman, but actually he grew up, he was a descendant of Lithuanian Jewish parents in Philadelphia and moved to England on a scholarship. And this is the famous French mathematician Andre Weil, one of the great mathematicians of all time. Mordell proved about a century ago his great theorem that the rank is finite. Sorry, I have the title up here. So that over the rational numbers, you can get all solutions from a finite number. Now that's obviously difficult because in Ramanan's talk, he talked about an elliptic curve, a cubic equation over the complex numbers. And the solutions over the complex numbers form a complex torus. He said it was the quotient of C by a lattice. A complex torus as an abelian group is the product of two circles. And that's certainly not a finitely generated abelian group. You can't generate everything in the product of two circles by taking a finite number of things and adding them to themselves. But over the rational numbers, there are fewer solutions than there are over the complex and the reals. And the big theorem of Mordell is that the rank is finite. And he proved that for cubic equations over the rational numbers. And Andre Weil generalized it to cubic equations over number fields, or more generally to more complicated equations called abelian varieties over number fields. And we still have the open question as to whether the rank of a cubic equation or an elliptic curve can be arbitrarily large. We don't know. I gave you examples where the rank was 0 and 1 and 2 and 3 and 4, but the computer's been looking and it hasn't been doing too well. The largest example that we know to date was found by a colleague of mine, a very talented colleague and a student of mine too, Noam Elkies, who's a professor at Harvard. And he found a curve, and you can see the coefficients are fairly large, but again, not that bad. And it has rank 28, and here are the 28 generators, the x and y coordinates, and the x and y coordinates in this case are all integers. You don't have very complicated rational numbers at all. And when Elkies found this example, it was going from year to year, that every year we had a little bit more computing power, we could find a curve of larger rank, but no one's found anything larger than this for the last 5 years, and so it's been giving a number of us in the subject pause. And I would have said 5 years ago that, of course, you can find curves of arbitrary rank. It's just that the coefficients have to be very large. But right now, I would take the position that no one knows. And I should mention that Elkies and another mathematician I'm going to talk about in this talk are very talented musicians. He's an international composer, and here he is sitting at the piano. Okay. So I'm going to tell you about the modern theory of cubic equations or elliptic curves, which goes back to Birch and Swinnerton-Dyer, and I'll tell you what their famous conjecture is on the subject and try to motivate it for you. So these are two English mathematicians. You can see here they're in proper garden dress. This reminds me maybe of Madras during the Raj or something, and this was taken at Birch's wedding day, and he's on the right-hand side of this picture. Whoops, there he is. And this is Peter Swinnerton-Dyer, now Sir Peter Swinnerton-Dyer, and he was his best man at the wedding. They became good friends working on this problem together. And they made an estimate, a very good guess for what the rank was of a cubic equation based on the number of solutions modulo primes p. That's a whole new area of mathematics, and I'm going to tell you a little bit about how they came to that and what the conjecture is. And that's been the center of research for the last 50 years. They just had a conference, by the way, in England last year for Birch and Swinnerton-Dyer on the 50th anniversary of the publication of their paper, just like the 50th anniversary of this institute. All right, so let me just give a little background on primes before I do the number of solutions modulo primes. We all know that's a number bigger than 1, not divisible by any smaller number. And the primes start out like this. I noticed that they were inscribed outside on the board on one of the illustrations. And a big theorem in Euclid is that this list goes on forever, that there is no largest prime number. There are infinitely many primes. However, there's no known way to produce the next prime. That's one of the great mysteries of number theory. So the largest prime that we now know is a Mersenne prime, which has almost 13 million digits. I'll give you an idea how large that is in a second. And one of the great theorems in mathematics is that even though the appearance of primes is highly irregular, the growth of them on average is quite regular. So here's a graph for the numbers less than 500, and I've indicated how many primes there are on the left-hand side, and you notice this is a very regular graph, and that's essentially the content of the prime number theorem, proved by Adhemar Vallée-Poussin. So here's an example. Here's a prime number that has about 3,000 digits. That's a Mersenne prime. And we have very good tests for primes. Now, what does this prime number, which has 13 million digits, look like? Well, I did an exhibit a few years ago in Paris with a wonderful Japanese installation artist named Ryoji Ikeda, and he successfully printed out two numbers of 7 million digits. He required a grant from Hewlett-Packard to get a machine that could print these out. And the numbers which have 7 million digits look like this. They're on a piece of paper about as wide as this podium. And they go from that wall to that wall on the paper. And the digits are 3 pixels wide and 5 pixels high, so that you need a magnifying glass, if you're my age, to read them. And one of the numbers he printed out was a randomly generated number, and the other one was a Mersenne prime, the 41st Mersenne prime. And I actually took the magnifying glass down and checked the last 400 digits of the one he claimed was a Mersenne prime to make sure he wasn't lying. And it's unbelievable when you look at these numbers. They're just they're just fields of gray on a white piece of paper. It's just, I mean, even this number, what does it mean? What does it mean? And yet, there's so much richness in prime numbers. In any case, when the French mathematicians came to see this exhibit, many of them had different reactions. And my favorite reaction was from Jean-Pierre Serre, who said that he didn't want to think about a prime number that way. He wanted to think about it as a P. Because if you thought about it as this long string of paper with numbers on it, you could never prove anything about it. All right, now, as I say, determining that a number is a prime can be done very quickly. And in fact, there's a great theorem that was proved by 3 mathematicians at IIT in Kanpur in 2002, that the testing of primality can be done in polynomial time. On the other hand, we also know that if it fails the primality test, it's much more difficult to factor a number. We don't know that, but it's suspected that it's not something that's in P. And here's an example. I said that prime numbers, we can test that prime number of 13 million digits is prime in almost no time at all, less than a few minutes, whereas this is an RSA number which has only about 250 digits, and the factorization of it into 2 primes, which have about 120 digits each, was considered one of the greatest achievements of computational number theory. And that's why so many codes are built on this trapdoor phenomenon, that it's more difficult to factor a number than to test its primality. All right, well, now let's get back to elliptic curves. And what do we mean by solutions of a cubic equation at a prime number P, or as we might say, modulo prime number P? Well, let's take this equation, y squared plus y is x cubed minus x. And now take xy to be 3 and 1. So if you try that in the equation, you see x cubed minus x would be 27 minus 3, which is 24. Y squared plus y would be 1 plus 1, which is 2. So 2 is not equal to 24. But it is a solution at the prime 11, because we say something is a solution if the left-hand side and the right-hand side have the same remainder after division by that prime. And 2 has the same remainder after division by 11 as 24. So 3, 1 would be a solution at p equal 11. And it turns out that if you want to see if an integer is a solution, if the 2 sides have the same remainder, it only depends on the remainder of x modulo that prime and the remainder of y modulo that prime. And there are only p possible remainders of x and p possible remainders of y, right? And so you only have to test p squared things, and you test those p squared things, and you see which ones give solutions and which ones don't. So there are infinitely many solutions because it's less than p squared. And here's an example I've printed out for you where you took this equation, and the first is for p equal 23. You see there are 23 things for x and 23 things for y. And I've indicated by blue dots which ones actually give the same remainders on both sides at 23. And there are 22 solutions. And here's for 71. And there's 71 things for x and 71 things for y. And I've indicated by blue dots which ones give the same remainders. And so you count them and you get 63. And so for every prime number p, you can take an equation like this and count the number of solutions mod p. And then the mathematicians discovered after Emil Artin's thesis in the 20s that it was best to write that number of solutions as p plus 1 minus an error term, which I'll call ap, little ap. P plus 1 is the number of solutions you'd find on a line, modulo p, the number of points on the projective line. And so since this is a curve and not a surface, you wouldn't expect p squared solutions. That would be almost ridiculous. It should be on the order of p solutions, and this is the familiar way of writing it. And we then define an object that Birch and Swinnerton-Dyer introduced, although it had been studied a little earlier, called the L function of an elliptic curve. And that's a function of one complex variable, or one real variable for all we need. And it's given, all it does is it encodes the information of the number of solutions at primes for every prime p. There are infinite number of primes p, so it's an infinite product. And you write it as it's called an Euler product because this is the factorization that Euler found for the zeta function. You count the number of points, you calculate this error term AP, you make a little term in p to the minus s by putting it in this way and inverting it, and when you expand that product out and take the product over all primes p and use the theorem of unicity of prime factorization so that every integer n is uniquely a product of primes, you can gather that into a series, an infinite series, summing over the positive integers, n to the minus s, where the an's are integers related to the APs, obviously, and that's called the Dirichlet series. And this is the series that Birch and Swinnerton-Dyer introduced. And all it does is it encodes the number of points mod p for every prime p. Now, of course, this definition, since it's an infinite product, if we want to think of this as a function of s, it only makes sense where the product converges. And it's not difficult using some standard estimates for this AP to show that it converges where s is bigger than 3/2. If you're doing it as a real variable, that's enough. If you're thinking of it as a complex variable, it's where the real part of s is bigger than 3/2. And it converges in that region, and so you can only really evaluate this product in that region. And here I've evaluated this product in a region for that curve y squared plus y is x cubed minus x, and you get this function. But beyond 3/2, you really can't say what its value is because the product doesn't converge. Okay? Now, on the other hand, there's nothing wrong with formally setting s equal to 1 in this product, right? I mean, we have this product, it's a function of s. Each term makes sense as a function of s. So I can put s equal 1, which is not in the region of convergence, into the product and evaluate what I get. And when I do that, and I rearrange terms, I just get the product of p divided by the number of solutions at the prime p. Okay, now, here's the big idea. If the number of solutions is large on average compared to p, then you'd expect this product to go to 0, right? I mean, your product of terms which are less than 1. And the larger it is on average, the faster this product will go to 0. Now, when will the number of solutions at p be large? Well, if I had a lot of solutions over the rational numbers, and I looked at those solutions at the prime p, that would give me a lot of solutions at p. And so the basic idea of Birch and Swinnerton-Dyer is that the larger the rank, the faster this infinite product should go to 0, or the faster this function should go to 0 at s equal 1, which is not in its domain of convergence. So here's an example. I took this curve of Elke's. Now this curve of Elke's with rank 28, the coefficients are enormous. But if you take the remainders when you reduce the mod p, they're just tiny little numbers, so you can count the number of points mod p. And I took this product and I took the product over the primes, say less than 100, and I evaluated it for the primes less than 100, less than 200, less than 300, less than 400. And you can see that this product goes to 0 very quickly. Because the rank is 28, you get on average a large number of points mod p. These terms in the product are all less than 1. The more you take, the faster it goes to 0. Okay, so that was the heuristic behind Birch and Swinnerton-Dyer. That if you could only evaluate this function at 1, where you can't, that the larger the rank, the faster this function should go to 0. And they made computations based on that, and using finite terms in this product. And finally, they formulated the following actual mathematical conjecture, which is not just waving your hands, but is a precise statement. First of all, that this function, which was defined by an infinite product, has an analytic continuation to the neighborhood of s equal 1. You have to know a little complex analysis to know what that means, but there's a way of extending the function. There should be some way of extending the function beyond the half-plane real part of s bigger than 3/2, where you can't use the infinite product anymore, but there should be some way of extending it to get it to s equal 1. And the second part was, once you had it near s equal 1, then the order of vanishing should be equal to the rank. If you have an analytic function at a certain point in the complex plane, you have an invariant, which is the order of 0. And we saw that that order of 0 should go up the more points we had. And that would give a way of calculating the rank if you just knew the number of points at primes p for every prime p. And the third, to go even further, once you have the order of vanishing of a function, why not guess what the leading term is in its Taylor expansion at s equal 1? And they gave a beautiful formula for that, well, aided by Tate. They gave a beautiful formula for that in terms of arithmetic invariance of the cubic equation beside the rank, which are more subtle than the rank. So the most subtle of those invariants was a group actually called Shah, under the Russian letter Shah, given by Tate, which was studied simultaneously by John Tate, my thesis advisor, and Igor Shafarevich, a great Russian number theorist. And this was studied in the 60s. And this invariant measures essentially the difference between finding a rational solution and finding a solution at p for every prime p. And both Tate and Shafarevich conjectured that this thing is finite. And its order appears in this leading coefficient in the Birch and Swinnerton-Dyer conjecture. So you have this amazing conjecture, as Tate once said, about a function which is not known to be defined at s equal 1 in terms of the order of a group which is not known to be finite. And here's a picture of Tate and on this side, John and Igor Shafarevich in the 60s at the time they did their work. They're both now in their 80s. Well, now I'm going to tell you what happened. So the Birch and Swinnerton-Dyer conjecture was formulated 50 years ago with these refinements due to Tate and Shafarevich. And for a long time, the only work on it was really computational work and compatibility with other conjectures. But then in the 80s and 90s, there was some serious progress, and there's been, so I'll summarize that. The first thing was that part 1 of the conjecture. Remember, there are 3 parts. You need an analytic continuation, then you have to study the function at s equal 1. So the analytic continuation was obtained by Andrew Wiles and Richard Taylor in '95. And they actually proved that if you replace this Dirichlet series, the sum of a(n) to the minus h, which encodes the number of points, by this function of the variable tau in the upper half plane, like Ramanan used in his lecture, that you got a modular form. That was the so-called modularity conjecture, which people attribute to a lot of different people. Taniyama, Goro Shimura, Andre Vey. In any case, it was proved in this situation. Here's a picture of Andrew on here and Richard Taylor over there. And this was the key ingredient to the proof of Fermat's last theorem. Well, it was one of the key ingredients. There were many ingredients in the proof of Fermat's last theorem, but the modularity of the L function of an elliptic curve was absolutely critical. Well, once you have it extended to s equal 1, you can study it there. And I proved the limit formula with Don Zagier in 1983, and then using that and some wonderful work of Victor Kolyvagin in 1986, we can now combine to show the following. If the L function is non-zero at 1, then the prediction is that the rank is 0. So we can prove that. Rank is 0, so there are only finitely many solutions. And if the L function is 0, but the derivative is non-zero, then we can prove that the rank is 1. So that gives a criterion for finding infinitely many solutions. And in fact, the formula I found with Zagier actually produces a infinitely many solutions. And that's how we found that insane point, which had 5,000 digits in its numerator earlier in the lecture. And in both cases, not only can we prove that the order of vanishing is correct, but we essentially can prove the entire Birch and Swinnerton-Dyer conjecture. In particular, we can show that Shah is finite and it has the right order, as predicted they did. And here's a picture of Don Zagier when I worked with him in the 80s. And here's a picture of Victor Kolyvagin. Kolyvagin was a student of Shafarevich at exactly the same time that I was a student at John Tate. So ideas just get passed down from generation to generation. I should say a bit about Zagier. He's an amazing mathematician. He's a child prodigy, among many other things. And he finished high school in the United States at the age of 13, and he wanted to go very much to Oxford. So he took his A-levels and his O-levels and all the necessary nonsense to get into an English university. And then after he applied, they told him that they couldn't take him because they did not accept an undergraduate under the age of 16. So he went to MIT. He finished MIT in 2 years, and he applied to go to Oxford as a graduate student at the age of 15, where they took him because there was no problem taking a graduate student at the age of 15. He finished graduate school at the age of 18. At 19, he was a full professor at Bonn, internationally famous mathematician. And I met him when he came to Harvard, and I was a graduate student, and he was younger than I was, and he was a distinguished visiting professor. And at that point, I decided that life was really not fair. Now, one thing that's amusing about this is that we can only do the cases where the order of vanishing is either 0 or 1. You think when the order of vanishing is greater than 1, that's when the rank is supposed to be 2 or 3 or 5 or 28. That should be easier to produce solutions, but no one's been able to find a way of producing specific solutions using the L function. And we can't prove anything, but the computer has been a great guide, like it has been for all questions in number theory. And here's a summary of the evidence for the simplest curve of rank 2, which I had put up before, y squared plus y is x times x minus 1 times x plus 2. We know that the order of vanishing is 2, and that all primes except 7 or 8 up to 50,000 do not divide the order of Shah. The predicted order of the Tate-Shafer-Levitz group in this case is 1. So it shouldn't be divisible by any prime, but we can at least check this for a lot of primes. And this computational work has been done by William Stein, who's shown here on his skateboard. Notice how the method of dress has changed for mathematicians since that picture of Birch and Swinnerton-Dyer and the picture of, I should say William is an expert, besides a great computational number, a very good skateboarder, and he helped me prepare many of the slides for this talk. And I'm going to finish with some recent progress that's been made, which I think is really exceptional, and that's on the average rank. And this progress was made in the last 3 or 4 years by Manjul Bhargava, and he doesn't study the rank of any individual elliptic curve, or any individual curve over the rational numbers. That's too hard. He calculates the rank as you go over all of them, or as Ramanan might say, over the moduli space. Here's a picture of Manjul. He's an exceptional young mathematician. I had him as a student when he was an undergraduate at Harvard. He's now a distinguished professor at Princeton University. Many of you may have seen he just won the Infosys Prize in mathematics, and he was interviewed by CNN. He told me that the interview lasted 3.5 hours. They had him play tabla. He's an expert tabla player, I should say. He's another musician. They had him play tabla, they had him juggle, they had him do Rubik's Cube. Probably all that will be in the TV, and they'll cut out all the mathematics. But in any case, let me at least tell you what he did, because it's really fantastic work from a completely different angle, which doesn't look at the number of solutions at primes p at all, but uses other analytic methods. So the first idea he had was that one should be able to find a systematic way of enumerating the cubic equations. And we know that it's a countable set because every cubic equation has rational coefficients and the rational numbers are countable. But he found a very efficient way of enumerating it, that every curve has an equation of this form, where a and b are integers, and you can even make it unique if you assume that they're not divisible by high powers of primes. And then he defines the height of the curve as the maximum of the 2 positive integers a cubed and b squared. So if you fix a height, there are only finitely many cubic equations which have height less than that, because you're bounding the size of A and you're bounding the size of B. And you can also show that for, well, I just say there are finitely many less than x, and the number, if we call it nx, grows about the same speed as x to the 5/6 power, because there are x to the 1/2 values of b with b squared less than x, and x to the 1/3 values of a with a cubed less than x, and then you only have one condition, that the discriminant of the equation be non-zero. So you have for every value of x you have a finite number, but the number goes to infinity with x. And so you can define average rank in the following way, and this is a perfectly precise mathematical definition. You take the limit as x goes to infinity of 1 over the number of curves of height less than x, and for each curve you put its rank, which is some integer. And if that rational number converges to a fixed number as x goes to infinity, you call that the average rank. So we suspect that this limit exists. Nobody can prove that this limit exists yet. And not only that, we expect that it's equal to a half. In fact, we think that half the curves in the sense of probability have rank 0 and half have rank 1. But what Manjul was able to prove with his student Arul Shankar, and I believe Arul is a student originally from Chennai, they've just shown that there's an upper bound on this limit, And moreover, namely there's a lim sup, and that the upper bound is less than 1, which is a remarkable result because no one prior to this was able to prove that the average rank was even finite, or even define it. So first of all, they defined it, and secondly, they've proved this wonderful result about it. And the methods use other analytic methods in number theory called geometry of numbers. In fact, Mongeau has reinvigorated this subject in a way that can really only be comparable to the work of its creator, which was Hermann Minkowski. I mean, what he's done to this subject is just incredible. And this is just one application. I've been working with him on a subject which Professor Ramanan really started, where we're not only doing cubic equations, elliptic curves, but also ranks of the Jacobians of hyperelliptic curves and the number of points on it. So the method is ultimately very flexible and will apply to a lot of other situations. And I think this is the most interesting development in the subject in the last 25 years. So that finishes my talk, but I wanted to put up my photo that was taken in 1971 in Chennai. Here I was with a lot more hair, a student of Carnatic violin. And I want to say how much the stay here meant to me, because I was reading a lot of mathematics at the time on my own, and my teacher said to me after a few months that I had some talent in violin, but he thought my talents probably lay in mathematics. So I went back to that. Thank you very much.
Time for remarks or questions or
This is simply impressionistic. You wrote a formula 1 over 8x times some.
Yes. Let me get back to it.
It looks very similar to the formula which comes in discrete trace of operatives.
Yes, yes. So this is a new subject for us, but it's an old subject. I mean, it's now, Barry Mazur, my colleague Barry Mazur, who's also done wonderful things on elliptic curves, calls this new subject arithmetic statistics. And it's really modeled on finding means, finding deviations for arithmetic quantities, which we've never thought of before as a mass of quantities. We've done it in one case. And we focused all our attention on one cubic equation and its L function and the conjecture of Birch and Swinnerton-Dyer for it. Whereas this new point of view is, no, that may be too difficult. Let's do all of them and do probabilistic study. And so we're borrowing a lot of methods from statistics and arithmetic statistics.
Who was the music teacher who asked you to go back to mathematics?
I don't know. So I'm hoping to find him, in fact, on this visit. But I can tell you my experience. I arrived. I played classical violin and viola, and I arrived. I had an introduction to study Carnatic violin, which I knew nothing about, of course. But I was told I was playing on the same instrument. How difficult could it be, right? And so I showed up at this wonderful man's place, and I imagine he's now in his mid-70s or 80s. I looked at all of my papers to try to find his name. I couldn't. But in any case, he had a school. And he said to me, well, have you played Carnatic music? I said, no, but I'm a master of the violin. And he said, well, just come back this afternoon. I have a good class for you to join. So I came back that afternoon, and there were a bunch of 5-year-olds, and I started with the 5-year-olds. And then I moved up to the 7-year-olds. That's how far I got. And it's an amazing music. Do any of you know the story of how the violin came to be used in Carnatic music? It's a great story. I mean, at least I was told this, that it was taken from a Portuguese ship that landed in Goa. And they had a fiddler on the ship. And the musicians in India recognized that the instrument was better than the instrument they were using. And so they completely adopted it. I mean, it's tuned differently, it's held differently, it's bowed differently, everything is different, but the instrument is the same instrument. And I was told it was from the first arrival at Goa. Yes?
Here you say that on average half the curves have rank 0 and half have rank 1, but you do not know whether it's bounded. So do you think it kind of decreases exponentially? Or? There
are a lot of estimates for that, and it's a great question. we believe that, let's see if I can say this intelligently. There are some statistics for the, you see, as I say, this nx grows like x to the 5/6 power. So if I took all the curves of height less than x, which had rank greater than or equal to 2, the claim is that grows slower than x to the 5/6 power. And there are some guesses as to what power that grows, and what power times what power of the log. But since we can't even prove this guess yet, we can't get to the second term. But there are all these beautiful second term expressions, just like in classical statistical physics, that are coming into this subject. And Bhargava is one of the leaders. Another young mathematician at MIT, Bjorn Poonen, is a great leader in this subject. And I think we're going to see vast numbers of results of that nature come out in the next 10 years. But right now, I should say the computational evidence does not match this theoretical stuff. We haven't gotten far enough out in the computations for them to converge to this kind of behavior. So computationally, before Bhargava's results, it looked like a positive percentage of curves had rank 2. It looked like that, you know, from all the evidence that we had on the computer. Whereas now we're almost certain, well, based on this, it never happened.
Following on the last question, you raised the question whether there's an upper bound to the rank. Is there any hope of answering that from this kind of statistical?
No, absolutely not. Absolutely not. We have, it's just, the problem is that the statistics don't really estimate the rank. The statistics estimate another group which bounds the rank called the Selmer group, which is introduced by Mordell and Vey. And the Selmer group has two parts. It has the rank, and it has this part that's the Tate-Shafarevich group. And we get very good arithmetic statistics for the Selmer group, and we can show that those groups can become arbitrarily large, but we don't know whether it's the part that's coming from the rank or the part that's coming from the Tate-Shafarevich group. So that still remains completely mysterious, which is good because there's so many good problems for these young people to work on here, right? Yes?
One of the solutions which you showed, which had 54 digits, the equation which you had was y squared plus y on one side, on the other side.
It's huge.
X cubed.
Right.
But you had huge digits, and also x squared term on the right-hand side was missing. Is there any rationale behind the choice of these huge coefficients for?
Yes, thank you. So how did Elkies and other people find these curves that have rank, very large rank? So they took the Birch and Swinnerton-Dyer conjecture and they ran it in reverse. Namely, they said, if a curve has very large rank, you'd expect it to have a large number of points modulo the first few thousand primes p. So why don't we, for every prime p, identify the equation modulo p that has the maximum number of solutions. I mean, it can't be bigger than p squared. So we just look at all the possible equations, and we find the equation mod 2, mod 3, mod 5, mod 7, mod 11, mod 13 that have the maximum number of solutions. And then we use the Chinese remainder theorem to produce integers, very large integers, that reduce modulo p to all of these coefficients. And so we've ensured that for the first 1,000 primes p, not only do we have a large number of solutions, we have the largest number possible. And then you go look for rational solutions. And that method worked up to 28, and then it ground to a halt. And we don't know why.
What is that? NX there? NX.
The one back?
Yeah, there. No. What is that? NX there?
Nx is the number of curves of height less than x. So it's basically the sum of the rank of E divided by the number of total curves.
So instead of rank, if you put torsion, order of the torsion.
That goes to 0. In general, there's no torsion. But what Bhargava really proves, now that you've asked it, is instead of putting rank here, he puts the order of the two Selmer group. That's what I said is this group that sort of sits between the rank and the Tate-Shafarevich group. And he proves that that limit exists and is equal to 3. I mean, all the results are very precise. It's not that it's just less than 1 or something. He actually evaluates limits, but not with the rank there, but with a group that's a little bit larger than the rank.
there are no more questions, let's thank them.
Thank you.
I have some small announcement to make after this wonderful lecture. We will break for lunch. We will have almost 2 hours gap. But at 3 o'clock we have an important meeting. Our chairman of our board, the Honorable Minister for Education, is going to be coming here and unveiling the foundation stone. So you are all requested to be here at 3 o'clock. And our next program for public lectures will begin at 4:15. So please be here at 3 o'clock. Thank you.